we want to welcome everybody to our Tetra Tech High Performance Buildings Group recommendations for healthy buildings. We're releasing these today for public comment, and we'll be posting them on our website and distributing them throughout our firm and to many of our clients so they can provide us additional feedback. Next slide. We are recording today's event, and we know that it's important to our clients. This is just one example, the project that we showed you in the cover slide. You can see that they're advertising this project as the best indoor air quality in Los Angeles. And we're finding this is an important subject for all of our clients going forward. And people are continuing to contract COVID. Even our own Dr. Bahnfleth and Doug Mass both recently contracted COVID. There's many others on this call that have contracted COVID. So it continues to be an important issue as people return to work. Next. We also want to thank all the invited guests. We know some of you are joining today, but many of you will be seeing this recording. And again, we would appreciate your comments and feedback on our recommendations. Next. So our agenda today, we have introductions and acknowledgements. We're starting off with Dr. Bahnfleth providing an overview of MYTHBUSTERS about some of the information that's been inappropriately distributed and what the facts are. And we use those facts in developing our recommendations that will be presented to you by 5 experts around the world. And then we're going to finish up with question and answers led by Travis English from Kaiser and Randall Brobson from Goldman Sachs. Next. Our goal for establishing the task force back in March of 2020 was, first, we wanted to lead the industry with science. We wanted to make sure that we had the facts on what we were telling our clients. Many of our clients had to operate 24/7 through the pandemic as an essential business. So they didn't have time for any myths. They needed the facts on how they responded. We wanted to make sure that we had experts in indoor air quality and environmental control. We wanted to act locally, meaning use our global expertise, but with local application, because every local district has its special requirements. We're using this as internal training, and this video will be distributed to all of our staff throughout our 3,500 people within the Tetra Tech High Performance Buildings Group. We'll also be sending these to clients and making presentations so they're up to date on our latest recommendations. And ultimately, it's not just about the pandemic and COVID-19, it's about creating healthier buildings that reduce the chances of catching cancer and improving productivity and well-being in the building. Next. Want to introduce our expert speakers today, Dr. Bahnfleth from Penn State University, Alec Roger, he's in Perth, calling at 11 o'clock at night. Dr. Andrew Billmore, he's in London, he's going to speak about specialty controls. Brian Berg in Los Angeles will speak about ventilation. Mr. Mass, an expert in high-rise office buildings and residential towers, going to be speaking about recirculation air rates. Justin Downey from RWDI is going to be talking about different types of air distribution, which ones are effective. And Stephanie from Safe Trace is going to be talking about certifying buildings, including new UL certification. We also had a number of other experts that we wanted to acknowledge. And one name that's not up here that I did want to acknowledge today is Amy Kwan. Amy's done an amazing job in organizing this entire presentation, taking feedback from everybody, getting the calendar invites out, and getting all the information. So thank you, Amy Kwan. Next. These are our client panel speakers. You'll be hearing from them at the end. Next. I mentioned earlier about the importance of healthy buildings. This is the latest study by Honeywell, and it's definitely on the top of mind of people. So we want to dispel any myths about healthy buildings. And with that, next slide. We're going to turn it over to Dr. Bahnfleth for the next 15 minutes, and he's going to dispel a lot of myths that he's learned about over his years following this pandemic. And he recently returned from Rotterdam, where he did contract COVID, but I understand, are you okay now, Dr. Bell?
Yes, I just tested negative for the first time yesterday, so it seems to be about done.
And are you heading to Finland?
And I'm leaving for Finland tomorrow for the Indoor Air Conference, where
I
they're
mean,
doing a
he's
lot of
really
things
been a
different.
trooper. He's been a trooper. So thank you, Dr. Bill. We appreciate it. With that, go ahead. Next.
Okay, thanks, Steve, and glad to be with everyone. Uh, this was a topic that was suggested to me, and I've really enjoyed putting a few things together. I've got, I think, 8 myths that came to mind as being very common ones that that come up, but we could have a much longer discussion of different ones if people want to ask other questions. And I like to start discussions like this with one of my favorite quotes from Josh Billings, who was an American humorist of the 19th century, maybe sort of a Mark Twain, but not quite as well known. And then he said that it ain't ignorance causes so much trouble, it's folks knowing so much that ain't so. And I think we've all had many opportunities to observe that during the pandemic with all of the different uh, descriptions of how technologies work that have been thrown out and how exposure happens and whether we can or can't prevent infection. So I'll leave you with that, and maybe you'll be using this quote one of these days yourself. So let's go on to the first one. So the first myth that I think is really important to understand is the notion that if we just design buildings correctly, the occupants are going to be safe from COVID and other diseases. Um, there are a lot of reasons why this isn't true. We can never really reduce risk to zero, and we certainly can't do it simply by the way we design a building. One factor is that there are multiple modes of transmission. Inhalation has come to be recognized as one of the most important with respect to COVID-19, but there's also droplet spray, which occurs at close quarters, and there is not a whole lot you can do to prevent transmission if you're standing half a meter away from someone and speaking to them and having their respiratory emissions, directly going into your eyes, nose, and mouth. And then there's also touch and contact. So for various reasons, we can't design the building to do that. HVAC systems, which we've talked about a lot, primarily affect airborne transmission. And so the best we can do is to reduce risk by some certain amount. And what that tells us is that we have to understand where HVAC and the building design fit into the overall picture of risk mitigation. And so risk assessment is really critical to properly allocating resources effectively. Next. So the next one is that an outdoor air or more outdoor air is the best way to reduce infection risk and improve indoor air quality. And uh, things tend to get simplified when the public is discussing things like COVID risk mitigation. And we've kind of boiled the discussion down to how much outdoor air, which really isn't the right way to think about it. And again, I note the hierarchy of controls in the upper right there. Engineering controls, including ventilation, are only one slice of that. And we know that there are public health measures that are significantly more effective than anything we can do once we actually have an infected person in the building. So vaccination, of course, very important, even though it's not perfect. And we know that distancing and wearing high performance masks, N95s or was it FFP2s, those sorts of masks are effective. And amongst engineering controls, we don't have only outdoor air. We've got control of airflow, which will be discussed, and mechanical filtration, removing particles, and germicidal UV. So we've got a whole toolbox that we can use. And as the lower right figure shows, um, there is good evidence that improving filtration efficiency and removing more particles from the air that way is more cost effective than increasing ventilation rate. And there are really no one size fits all solutions, although we can formulate some useful general guidelines. Next. The next myth is that we know what outdoor air flow rate is necessary to effectively control infection risk. We'd love to be able to say that we figured that out, but there has been a lot of study of ventilation rates and infection risk, and the conclusion from one of the best systematic reviews by Hugo Lee and others is shown there. Strong and sufficient evidence that there's a connection between ventilation and infection transmission, insufficient data to specify and quantify minimum ventilation rates. It's just hard to do the research to pin this down, and especially when we have diseases that inconveniently refuse to transmit by a single mode. If they only transmitted by inhalation, we could probably control it, but many of them can transmit in all three of the ways that were noted. So this partitioning for different pathogens is different. Some of them really don't transmit by air, and it's touch that's the problem, and we can't do anything about that with ventilation. Also, we have to note that the idea of how much ventilation is enough is tied into our notion of acceptable risk, which is a long discussion in itself. But do we want to protect the public by reducing the R naught to less than 1 so a pandemic or epidemic dies out? That doesn't mean you won't get infected. It just means overall there are few enough infections that the epidemic's going to end. Or do we want our view of risk to be, if I'm in this room with an infected person, I have a very low risk of being infected? So there are a lot of unanswered questions about where we draw the line as to what we're trying to accomplish with outdoor air. Okay, next. And another important one is that getting the right amount of outdoor air to the space is all that matters. Again, our discussions have kind of boiled down to, well, how many air changes of outdoor air do I have? Or how many CFM or liters per second per person of outdoor air do I have? And I think one of the things we've learned, and those who've been trying to do risk mitigation for the last 2 years, is that it's not only that amount of outdoor air, but it's how we get it to where it's needed. So air distribution, which is coming up in the other presentations, is very important. We've got overhead mixing, which tends to produce uniform concentrations, although it doesn't always exactly do that. We've got various kinds of stratified distribution, displacement, underfloor, stratum ventilation that have been shown to have some really good qualities in terms of removing bioeffluent and removing building-generated contaminants, but that have really kind of an Achilles heel, perhaps, when it comes to dealing with exhaled infectious aerosols. And then, of course, natural ventilation, which can be very sketchy. Lydia Maraska said at the conference a couple of weeks ago, where she also got infected, that natural ventilation is no ventilation unless you're very careful about how you do it. And there's also personal ventilation. So we have a lot to learn here and a lot of possible ways of approaching this issue of how we distribute the ventilation air for dilution to the extent that we're relying on it. Next. All right, so one myth that I covered was that we do know how much outdoor air is needed for infection control. Here's another one, and that is that we don't know what outdoor air flow rate is needed for effective infection risk control. People who are hewing to either position as an absolute are wrong. We do know something about how ventilation rates or clean air delivery rates affect the risk of at least airborne transmission at a distance. We have the Wells-Riley model that's been used extensively during the pandemic, and there are many risk calculators that allow us to estimate the impact of ventilation rates on infection transmission. You can see the result of one study on the right. This is using actual particle removal data from an experimental research project together with the Wells-Riley model to estimate what the relative risk reduction is for increasing air changes from about 1.3 to 5. And you see there we get about a factor of 2 reduction in risk of infection by this route. So we can get in the ballpark, but we have to remember that there are many uncertainties involved in doing this. So we know something, but it's not highly accurate at this point. Next. And here's a fun one. I tried to come up with a myth here that wouldn't result in calls from attorneys. Manufacturers' claims about air cleaners can always be trusted. You know, this has been one of the main topics of discussion during the pandemic is, does technology X really work the way the manufacturer claims? Is it safe to use? How can I know if it's working in my building? So what we can say here is that there are many promising technologies, but a lot of research gaps about effectiveness and safety, especially for what we've come to call additive air cleaners. Most of them are reactive oxygen species air cleaners that put some kind of oxidizing disinfectant into the air. Fortunately, there's a lot of work going on to develop standards, but they're not there yet. I think we also lack application-relevant testing and certification procedures. So you're convinced that a certain technology works and you put it in your building. What do you do now, short of conducting epidemiological studies, to know that it's actually working? That's another big gap. And of course, we have safe traces here, and that's maybe one step in the direction of having methods that can be used to validate different kinds of air cleaners. So the picture is not great right now. I have to say that germicidal ultraviolet is maybe an exception here. Many probably know I've been doing research on it for over 20 years, but other people have been doing research on it for 100 years. And the photo on the right comes from a 1937 to 1940 school study done in Philadelphia that demonstrated very good results. So there are some technologies that I think are reliable, but even UV is somewhat lacking in standards and certification. But I think these things are going to be a key to low energy, low carbon, high IAQ buildings in the future. So there's a lot of motivation for working on them. Next. Another fun one that comes up all the time is that fiber filters can't capture particles smaller than 0.3 microns. I've even heard this said about HEPA filters, and it really comes from a misunderstanding of rating procedures, which generally don't use particles smaller than 0.3. So it's become a common myth that because we're only testing down to 0.3 microns, that nothing happens below. But if we understand the mechanisms by which fiber filters remove particles, inertial impaction, the top, which is more efficient for large particles. So you have increasing impaction, the curve that goes upward to the right in the figure. And interception is a similar mechanism. We combine that with diffusion, which results in higher efficiency when we have small particles because they move farther under the influence of turbulence in the air. So we get curves that actually decline in efficiency to some most penetrating particle size, which is around 0.3 for a lot of filters, and then increases again. So we don't have to worry about that. These filters are actually useful for removing viruses and infectious aerosols. Next. Another important one is the idea that our air quality in buildings is okay, and it's just this new found concern about indoor infectious disease transmission that is a problem. And no, that's not true, and we've known that for decades. We've got plenty of research that suggests that higher ventilation rates would result in lower sick building syndrome symptom incidence and then less sick leave, that higher ventilation rates, if it's clean air, of course, would result in higher productivity. And if we go to the next slide, we also have plenty of evidence that if we have higher efficiency filters that remove more of the fine particulate matter in the air, that we could realize fairly substantial annual benefits in terms of morbidity and mortality, death and disease costs, even in relatively clean environments. Obviously, there are huge benefits to be achieved in places where the air is dirty, like Delhi and Beijing, but even in cities like London, Sao Paulo, still quite significant. So this is something that we ought to work on. So that's all I have, and I don't know how I've done with the time, but I can stop here and be happy to discuss other things that people are interested in talking about that are what they believe to be myths that need to be busted.
Dr. Bill, your timing was impeccable. You finished right on time, and I think it's a great opening to our presentation. And now we're going to start with the High Performance Building Group recommendations, which are based on the discussions you just had. And we're starting with Doug Mass, president of Costantini. Doug is really an expert on high-rise office and residential towers. He's been doing a deep dive with his clients about recirculation rates and what's most appropriate to provide the healthiest spaces possible. With that, take it away, Mr. Mass.
Thanks, Steve. Next slide, please. So we've spent the last 2 years meeting basically every week, including Dr. Bill and Steve and others on this call, to talk about how do we create the healthiest environment in the building. And just going back to the basics, what are the 4 main elements we always consider? Occupant density, environmental characteristics, what kind of space you're in, exposure time, and occupant activity. In other words, what is the health risk we're trying to protect against? And I think we all know these intuitively. And how do we make this into a recommendation or a guidance? Next slide, please. So let's talk about the basics. What are the givens? The givens are, we're assuming somebody in the space is sick and emitting viral droplets or bioaerosols. We're also assuming that any air we bring in from the outside is virus-free. And that's where we start. But the one thing we want to just mention, regardless of what we say today and recommend, the guidelines for masks, social distancing, and vaccinations, we believe we should follow local and federal and other authorities who are, and this we say it's a constantly evolving scenario, as we all know, different variants, et cetera. The next slide, please. So let's talk about effective air change rate. And just so everybody knows, and most of you do, air change rate is not just outside air, but it's the amount of recirculated air in the space. And as Dr. Bill said, there's no one solution that fits all. So what we've basically done is we've listened to a lot of people. We've done a lot of research. We have a lot of specialists working with us. And we believe that once you get into an office building space or any kind of indoor space, that the health of the building, the air quality, you get a superior air quality in the 4 to 6 equivalent air change rates. And you say, well, where does that come from? Well, it comes from a lot of specialists. For example, Dr. Joe Allen, Harvard School of Public Health, has published a lot on this. We've got a lot of data from other folks. And more recently, which I think was pretty exciting, is that Underwriter Labs, for those of you in the US, certainly, UL has sort of endorsed the 5 air changes as the basis to verify ventilation and filtration removal in a space. And I think at the end, Stephanie's going to talk about that a little bit. We're also seeing that where we can't get 5 air changes, let's say an enclosed room, et cetera, we may want to put a portable air filtration system in. The other part is we talk about ventilation rates, and this can be modified depending on where you are a little bit, but we're talking about around a 20 CFM per person. Now that's not per square foot, and we know densities and spaces have been on the decrease, not on the increase. So we're also talking about perhaps bring it up to 30 CFM per person to improve cognitive functioning, and that is also part of one of the studies from Dr. Joe Allen. But on the right side, I think it's very important. We have a lot of people from different offices around the country, around the world. While we're recommending 5 to 6 air changes, that there are local practices and legislative requirements in different countries that relate to energy consumption that will impact the use of more air changes in a space. So we have that debate going on right now, but local practice needs to be looked at, but we still believe 4 to 6 is the right area to be. Next slide, please. So what we do as a practice is we look at spaces for our clients, and we understand how do we get to those levels. So here's an example of a commercial building. We took a commercial building, we took a typical floor plate, and we looked at the amount of outside air, we looked at the number of air changes and the filters. So we started with a MERV 11 filter. That's what they had there. And we were just, if you look at the bottom, we were at like 4.49 air changes. And we said, what if we go up to a MERV 14, which is option one, and we can go close to 6 air changes. But what we're doing now is we're also looking at the energy use and the carbon, the amount of carbon that's being emitted. So I think that's very important, that it's not just about the air changes in the space, but we also have to look at the totality. Next slide, please. We're also doing this in residential buildings. We're looking at residential buildings not only within units themselves, maybe they're, within a family we're less concerned, but maybe roommates and other people. What kind of air change rate do we have in residential buildings, and certainly in amenity areas in residential buildings? And again, we've done other studies, and in some of the residential units where we're below the 4 to 6 air changes, we're looking at putting in a portable HEPA filter, and this can be brought in into a conference room, et cetera. And you can see in this particular example at the bottom on the left, the total was 6 equivalent air changes, which was pretty darn good. And we said, what if we added a 1,000 CFM HEPA unit and brought us up to 9? So I think this is my last slide, but I think what we're really saying is we believe that guidance of 4 to 6 is where we need to be today, but we have to balance that with the energy, the embodied carbon, and other factors. And again, one size does not fit all. So with that, I'll turn it back to Mr. Strauss.
Perfect, Mr. Mass. Excellent timing and a good presentation too. So thanks so much. Our next speaker is Brian Berg from Los Angeles. Brian has been consulting with global companies through the pandemic about what they need to do to protect their employees. So many of these clients are essential employers operating 24/7, 365 days a year. And he's really become an expert on how to provide appropriate ventilation. With that, Brian Berg.
Thanks, Steve. So as Dr. Bahnfleth mentioned earlier in the MYTHBUSTERS section, there's no real worldwide consensus on the amount of ventilation required in a building for a number of reasons. So we've split up our recommendations based on geography. In the United States, we're recommending 30% above ASHRAE 62.1 requirements. That's the 20 CFM a person that Doug was talking about earlier. This is in line with LEED and WELL building standards, and we feel is a good spot to provide a healthy indoor environment at an energy efficient rate there. When you're using this amount of increased outside air, we're recommending using demand control ventilation or other control strategies that look at the amount of people in the space and adjust the outside air accordingly to save even more energy. And then finally, ASHRAE 62, they came out with an addendum earlier this year that they've kind of defined what an acceptable level of ventilation is in a space. They've have a suggestion to actually question the occupants on their level of comfort in the space and if they find the indoor ventilation rates acceptable. And if 80% of the people find the building acceptable, then ASHRAE defines that as a well-ventilated space. So we feel that's the direction the industry is going, and something to think about as part of your designs. In the UK, the norm has traditionally been about 10 liters per second per person. During the pandemic, that's gone up to about 14 liters per second per person. This is something the British Council for Offices has been recommending. This is something that all our clients are expecting, all of their tenants are expecting as well. So this is really where the market's at. And this is that 30 CFM a person that Doug mentioned a little earlier. Australia, again, the norm has been 10 liters per second per person. That's gone up to about 15 liters per second during the pandemic. This is in line with Green Star ventilation thresholds. We've seen even higher from some of our clients. So these are kind of in our market spaces. This is where we're seeing the market at, and this is what we're recommending. Also, natural ventilation, if you have an opportunity to work with your client, do some studies to figure out if it's effective, this would be a strategy to use as well. So back to you, Steve. You're muted, Steve.
Sorry, next. Our next speaker is Alex Roger, calling in from Perth, Australia, where it's 11:30 at night there. So thank you for calling in so late. Alex is an expert in filtration systems. He consults with universities and researchers and laboratories on different filtration applications. He's going to be talking to you today about what types of filters remove unhealthy particles from the atmosphere and how you can use personal environments to provide a safer environment for challenging spaces. Take it away, Alex.
Thanks, Steve. So as the other speakers have already said, contaminant sources in the built environment can be either internal or from external sources, and how we treat them will impact on the indoor air quality within the environment. Outdoor intakes can provide a pathway to deliver contaminants into the building. As Doug mentioned earlier, they're generally considered free of coronavirus and particles, but they can deliver other external contaminants into the space, and I've listed some of them in the dot points there, and that's depending on both the building location and the intake locations for outside air. So outside air has to be considered as part of the HVAC strategy for a building design, but it's not the main thrust of today's discussion. What we want to talk about, the main contaminant source that we're talking about here, is the actual building occupant. So that's contaminants generated by the occupants within the building. So I can describe them as via the HVAC systems themselves as indirect airborne transmission. So that's where the air is transferred through the ducting system and can be delivered back into the space, and that's a very theoretical discussion. And the other one that we mentioned earlier is also improving personal environments with the use of in-room filtration to help counter direct airborne transmission, and that goes back to the graphic that Dr. Bill showed earlier around the close contact. So yeah, we'll go on to the next slide, please. So the ASHRAE application guide shows different range of building types, the typical filtration level, types of contaminants that are dealt with, and then what we want to do as part of our recommendations, the high performance building group is moving from a kind of typical MERV 8 scenario up towards MERV 13 as a minimum, and MERV 14 where possible. So MERV 6 to 8 really is an entry-level commercial building level of filtration. As you can see from the graphic there from table 12.1, it's unclassified in the filter performance range where the typical particle sizes will be. And then we move up into the MERV 13 and 14, and these are really classified around clinical environments and superior commercial office buildings. We want to be aiming towards achieving that MERV 13, MERV 14 provision that, as you can see from the graphics there, achieves a minimum 50 up to 95% efficiency through the different range of particle sizes noted on the table there. And the reason for upgrading, really looking at the significant contaminant reduction by achieving that filtration upgrade, improve the indoor air quality, and it captures the viral particles in the expected range at those higher filter specifications, and improves, as Doug was mentioning earlier, helps improve the overall effective air change rate within the space. Next slide, please. So the question is, how can we achieve this? It's about striking a balance between ensuring that we deal effectively with the relevant expected building contaminants and that they are suitably captured, maximizing the filter life, at the same time managing both the running costs and the energy consumption and filter replacement within a building system. Filter pressure losses in terms of a total system resistance are not insignificant and can sometimes be 20 to 30% of the total system resistance. And especially if we then move from kind of MERV 8 scenario up towards MERV 13 and 14, where the final filter pressure can go from 150 pascals up to anywhere in the region of 400 pascals. And we then got to make sure that that's not resulting in a trade-off of airflow to the space. Therefore, it has to result in an increase in energy. part of what we have to do is the key really is to choose the highest level MERV rating possible within the existing fan, motor and power limits that you have. And if that's not achievable, then we're looking at increasing potential fan upgrades, supplementary booster systems, more frequent filter replacement regimes, where you can actually bring forward the change of the filter rather than allowing it to get all the way to a fully clogged filter loading condition. So that's one of the other measures that you can actually use. They will result in a trade-off in energy consumption and running costs, but with a significant benefit. There are other energy saving measures, obviously, that can be done to counter that increase due to the filter increase, and those would have to be considered as well. Next slide, please. So one of the things that we have looked at, and we've got a green paper out on that, and there's a link to at the bottom of the slide there. Direct airborne transmission within an enclosed space can be mitigated against by the use of both in-room portable HEPA filters, and also potentially we start to see some of these coming along in new office developments where we're using recirculating fan coil units with a much higher filtration level than would be traditionally used in recirculating systems. They also potentially classified as low noise, smaller air handling units, but being able to deal with the increased filtration within the space. On the actual portable HEPA filters themselves, one of the things that we've noticed when we do on-site smoke tests, and Stephanie will talk later about that in more detail, is there's very little placement guidance that comes from the suppliers and manufacturers, so it can be a bit hit and miss in terms of the location, the effective location of them. So the personal environments document that we've published does give a lot of good right sizing and location advice on those in terms of improving relative performance. And anytime I've been involved in looking at commercial buildings in particular, I almost treat it like triaging the facility. So looking at where can in-room filtration be most effective. And I try to classify that in terms of the different levels there. High occupancy, high density spaces such as conference facilities, town halls, refectories and function rooms. Portable HEPA filters can be really effective there in increasing the indoor, especially if you have portable units, you can then move them around and make them use, especially when you've got in infrequently used, intermittently used spaces. Other areas are spaces with longer dwell times, so reception areas, waiting areas, smaller conference rooms and collaboration workspaces where people are likely to gather together in close contact for a longer period of time. That's also really important. And then also thinking more about, in terms of your office, commercial office layout, sedentary occupancy locations in open plan offices have to be considered, especially where they can potentially be in a location where a centralized return air grill is within proximity to them. So they're actually capturing all of the airflow within the open space, and it's passing past those fixed occupancy locations towards the return air. So they're actually in the direct airstream of the contaminant flow within the space. The other area where personal environments can be improved with the use of the in-room filters is areas where you actually already have poor airflow or there's a risk of stagnation. So that circulatory effect within the space where you're continually scrubbing the air will also help improve the indoor air quality within those personal environments. So to me, the message really is to triage the internal spaces using a risk-based approach in order to help use these systems to improve indoor air quality. And that concludes my presentation, Steve. Thank you.
Excellent, Alex. And the report, the green paper that Alex referenced, is in this presentation, which will be shared with everybody. So you will be able to click on that and gain information on these portable air cleaners. Next. Our next speaker is Justin Downey with RWDI. Justin's an expert in evaluating airflows in and around buildings, both using modeling and CFD modeling. He's going to speak to us today about different types of air distribution in spaces and some of the things that we need to be careful about as we move forward. Take it away, Justin.
Yeah, thanks very much, Stephen, and thanks to the Tetra Tech team for the invitation to speak today. As mentioned, RWDI does a lot of work in providing performance guidance. We don't practice in the realm of design works per se, but often called upon to help with some of the challenging problems with airflow, and air distribution is a major area of focus and concern for a lot of our clients and a lot of our design clientele. So I thought maybe a short orientation to the major classes of air distribution types that we see in the marketplace. The reason to get into this is, I mean, we're getting, some of this will be very familiar to everybody, but we get a lot of fundamental questions and concerns about understanding the nature of directional flow and movement in our spaces during the pandemic and now I think into the future. So 3 primary types and a little bit of characterization of each. Displacement ventilation. So the concept being to deliver air low in the space below the breathing zone, minimize mixing. So you're striving for a stratified directional flow of the air, which means you're trying to return that air typically high. Now, what really makes this kind of system stand out is the significant gradients that are in play. So you've got thermal gradient in play, which provides the directional flow. You've got the introduction of air, so some pressure gradients, but everything is moving in the vertical from low to high. The next is the most commonly used system type, which is your mixing system, typically characterized, although not exclusively, but delivering air high, maximizing the amount of mixing that is occurring in the space, essentially looking for air quality benefit through dilution. Return can be low or high, depending on the nature of the project and its particularly climate location and heating and cooling characteristics. Usually characterized by uniform conditions. So you're striving for maximum perfect mixing, uniform temperature, uniform pressure outside of the immediate throw of the supply, but looking for that consistent uniform condition. And the third one to remind is a bit of a hybrid. So not to confuse a displacement ventilation system with an underfloor air delivery or air distribution system. It's really a hybrid of the two, meaning that the intent is to deliver low, that's consistent with the displacement system, but you're trying to perform a degree of mixing in that breathing zone, in that occupied zone in the vertical, typically returning high. So characterized by uniform conditions in the occupied space and gradients above. If we go next slide, please. So if we think about these in just high level terms, what are the big pros and cons of each? And now this is speaking strictly from the sense of indoor air quality and the bridge between indoor air quality and contaminant control. The displacement system is a stratified environment. Its primary pro, again, not talking about energy or some other characteristics that can be pros for the displacement system, is the direction of movement. The idea that you would emit a contaminant, a human contaminant or other, and the direction of flow will minimize the potential that the individual across the room or next to you would be exposed, because you've decoupled the direction of flow from a potential path to exposure. The primary con of such systems, and I'll elaborate this on this a little bit more in the subsequent slides, is that these are vulnerable systems. They're vulnerable to occupancy patterns, equipment, exterior influences. I want to make clear that by expressing vulnerability, I'm not suggesting that these are not valuable systems for a whole host of reasons, but they can be vulnerable to certain influences. The mixing system pros are flexibility to increase dilution levels. So we've talked a lot about air change rates, both real and effective, outdoor air fractions today. The mixing system has as a clear pro, a lot of VAV applications, et cetera, the ability to increase dilution, increase your outdoor air, increase your total supply air, and enhance the solution in real time. Another pro is that it most readily accepts in-room or supplemental air filtration and such technologies. So because it's not it's a forced environment of mixing, it readily works with those other technologies, whereas it's a little more subtle, as I'll use in a minute, on the displacement side. And lastly, the UFAD, the semi-stratified system, again, a pro, the directionality of movement, a little more flexibility to tune the system, but then that also shows up as a con. You get into pressurization of the underfloor plenum and limits to that, as well as different diffuser options in the floor. But some flexibility is both a pro and a con. It does rely on a degree of mixing, and it can be a little difficult to increase ventilation rates. Next slide, please. So commenting more about the displacement system, and I hear, you know, from clients, from practitioners in design, there's a couple of camps emerging, and I wanted to dispel a little bit the need to get into this camp type behavior. Some characterize displacement ventilation as the ideal solution to deal with indoor air quality contaminants, and I don't think that's quite true. Others are expressing significant concern about those, and there's good grounds for that. What we do in RWI and some of our works is we remind people that these are subtle systems. And a subtle system, by that we mean you need subtle, predictable conditions for it to function properly. So that's typically characterized by a design that requires low velocity, and that relates to the energy question. Typically lower air change rates. Ideally, you've got very consistent and predictable heat sources, your people, your equipment. Those are known and they're not subject to high fluctuation. You've got consistent environmental loading. So if we talked about the internal gains, we can also talk about the external. So whether that's solar or the like. Consistent environmental loading in terms of airflow, so the influences of stack effect or infiltration, exfiltration, as well as making sure that you've got an appropriate height in a space for directional flow. Next slide, please. So trying to screen out, like we need to be smart about these things. We want appropriate application of the right kind of design. So looking for avoid scenarios or where to be cautious when deploying the displacement ventilation solution. Look to avoid long throw and spreading environments where you have certain question about the effectiveness of the ability for the displacement to spread across the floor. High air changes, which would result in both mixing, which, as we started at the beginning, is not desirable when you're talking about a displacement system. Avoid the mixing, also avoid the stagnation. So let's not ask our displacement systems to do the job of a high air change mixing system. Look to avoid highly variable thermal sources, that's people, equipment, seasonal heating and cooling sources, and solar gain. Avoiding highly transient people and equipment type spaces. So there's a subtlety to the displacement system that can be influenced by the movement of people, the transient nature of a space, again, low ceiling heights. Also, those things that are a little outside of the interior environment that can be influential on the airflow characteristics in the space. So am I vulnerable to stack effect, or do I have operable windows that I may or may not have control over? Am I dealing with special pressurization regimes or variable infiltration, exfiltration? So these are all flags to say, you know, is a displacement solution the right one for me in this case? Next slide, please. One of the critical risks that is flagged in the camp that suggests that displacement ventilation is not appropriate solution is the lockup phenomena. Essentially, this is a performance failure of a displacement ventilation system. The transition, if you're looking at the image on the left, the transition between the stratified layer and the mixing layer above that enables the return or the exhaust isn't performing as intended, and that would be driven by all the elements that I had outlined previously. When you have that performance failure, this lockup phenomenon becomes a real possibility, and it's essentially a concentration or accumulation of contaminants of a relevant size in that breathing zone. The two images that are in the center and the right give a reference point for what I'm describing. These are on the left is a uniform thermal environment showing the behavior of particles under a cough or sneeze scenario. And the one on the right is showing a thermally gradient driven environment where that lockup phenomena of the particles maintaining in a band in the breathing zone is demonstrated. So this is a real and viable concern. The vulnerability can be exaggerated when you're looking at a highly sensitive environment, particularly things things like healthcare, where bioaerosol control would be a major design driver. Next slide, please. But I do want to caution, I mean, there is cause for concern. There's cause for thinking about these with a great deal of care, but let's not throw out the baby with the bathwater, as the expression goes. We need to be smart about these things. We need to screen for those design conditions that might be unsuitable, and we need to study them very carefully. So this is a set of CFD results contrasting a mixing ventilation system versus a UFAD in the middle and a displacement to the right. And I'll focus on the displacement, which in this high performance CFD set scenario is performing wonderfully. But the nature in which like a design would have to probe to make sure that those conditions represented in an analysis becomes ever more important. So we know that these systems can be high performance, they can be effective, but they need to be really carefully studied. So our suggestion is, if you're going to be in that realm, then deep study is not just recommended, it may well be required. Next, please. Thank you.
Great presentation, Justin. Thank you so much. And I do think it enlightens all of us to the importance of evaluating these air distribution systems much more carefully as we move forward. Our next speaker is Dr. Andrew Bullmore. He's calling in from London, England today. He's an expert on control systems, and he's going to do a very short primer on how we can use control systems to minimize the energy as we provide improved indoor air quality. He'll be following up with a full presentation with other experts on September 22nd. Take it away, Andrew.
Thanks, Steve. A very short presentation. This, as you said, a very brief overview as how technology is increasingly being used to help drive better performance out of buildings. I'll start with the oft-quoted premise that, quote, you can't control what you don't measure. And so the first thing to be aware is there's an increasing plethora of sensors capable of measuring indoor air quality that are coming onto the market. Some of these are battery powered, some are mains powered, some are handheld, some are fixed, some are portable. There's a whole range, but they're becoming increasingly complex in terms of the range of parameters they could measure. So many of them don't just monitor a single parameter. Many of them will monitor CO2, NOx, VOCs, particulates, and some are even now being able to measure other parameters for indoor environmental quality, such as temperature, humidity, light, noise. And these aren't overly expensive. I'll come back to the expense of them and the robustness and the reliability of them before I end my talk. But just be aware that these things are coming onto the market and becoming readily available. One of the important characteristics of them, though, is many of them are IoT based. So in other words, they can feed real-time data straight into systems that can then to be measured and to take real-time actions. And I think it's becoming increasingly important that this real-time capability there, as we begin to look at the changing world in which we're living and the changing demands being put on buildings. And there I've mentioned there the idea of maybe some operating modes that might be preset operational modes that we might need to start thinking about. So normal operation, pandemic operation, air quality emergency, the prevalence of bushfires and wildfires was mentioned if you suddenly have a deterioration of air quality externally. And also low energy. How on earth do we actually maintain internal environmental quality, internal air quality, while enabling low energy performance of the buildings? We have to think about all of these things, and being able to have real-time feedback of how the air quality is being impacted by these different operational modes trying to deliver other outcomes is absolutely vital. And of course, one of the other things with real-time feedback is we can start to bring in the idea of real-time control, not just preset controls, but real-time control. So an example might be we're monitoring CO2 as a proxy for indoor air quality, and all of a sudden it goes through the roof. You know, that might trigger some sort of ventilation reset. And we have to bear in mind these sorts of things that we can now start talking about. So next slide, please. So if we go on to consider the idea of elevated CO2 as a proxy for reduced indoor environment air quality, one of the things that's come out of all the other talks really strongly is this fact that buildings exist as part of an ecosystem. There's the building, there's the fabric, the form of the building, There's the engineering systems, the environmental systems that help deliver the internal environments. But then we put people in those internal environments who interact with the building, and occupancy rates might create higher CO2 levels, just as much as maybe a poor performing HVAC system, or just as much in terms of the external environment of the buildings in, the air quality. So where we're getting to with technology is understanding that it's all very well just measuring, for instance, internal environmental conditions, but what we need to be able to do is relate that to all the other systems so that we can have robust evidence on which to base effective actions that we can take. Because we need to know how all these different systems are interacting, and that's where the technology is moving to, particularly in terms of composable platforms and digital twins. It's enabling us to finally pull together all the evidence that's needed to actually provide the robust evidence to deliver effective actions. And the one thing I'll finish on before I hand back is of course, robust evidence requires reliable data. And so the systems we put in place to monitor the parameters within buildings, including the indoor air quality, are absolutely essential. But reliable data does not mean every sensor has to be scientific, precision grade accuracy. It means it has to be specified and installed such that it's matched to the intended use of the data. And I really want to finish on that because people get hung up on accuracy. It's all about getting the systems right for the purpose you're intended. So I'll leave it there, hand back to you, Steve, and we'll follow up on the next presentation.
Great presentation, Dr. Bullmore. We're looking forward to your presentation on September 22nd. It's an important presentation because while I did not receive a death threat, I was accused of melting the polar ice caps and creating climate change by recommending higher recirculation rates. And so I think what we do need to do today is figure out how to use controls and technology to reduce energy effectiveness. So we only bring in more outside air when we need to. We only recirculate more air when we need to. And so I look forward to that presentation. Our final speaker today is Stephanie. She's with Safe Traces. She's going to be talking about how we commission and certify buildings to make sure that they're safe, and about a new underwriter's laboratory certification process. Take it away, Stephanie.
Thanks so much, Steve. Hello, everybody. So today I'm just going to briefly go over this quickly, and we're going to be talking about optimizing your HVAC systems and communicating your efforts to your occupants through building verification marks. So how do you do that? As Dr. Bahnfleth stated earlier, it's really important to measure and verify through risk assessment, and our technology, VeriDart, is actually used as a tool to do this. So companies like Tetra Tech and their high-performance building groups are using our VeriDart assessments to help their clients obtain HVAC optimization to simultaneously reduce airborne pathogen risk and reduce energy cost of consumption. So how do they do that? Well, aerosols are released into buildings to verify airflow, balance, and understand how quickly are aerosols being removed, identifying percent aerosol removal from a space through their ventilation and filtration controls. So our data is used to guide HVAC system operations, looking at percent outside air necessary, as Steve just mentioned, MERV filter levels, airflow, CFM, purge rates to reach optimization, and also, as Alex mentioned earlier before, understanding optimal locations of supplemental solutions like portable HEPA units by identifying airflows within a room and those impacts of those units and the optimal location to reduce those risks. But now we're being incorporated into commissioning and retro commissioning processes to obtain building verification. And this is where I'm going to run through that really quickly. So a lot of the strategy right now is, again, how is your building performing today? And so we run a baseline assessment to understand airflow. If aerosols are released in a certain spot, how far are they traveling? Is there isolation from room to room? It's basically like CFD modeling in real life using aerosols. And then, we're using this data to understand how quickly is the baseline system removing aerosols. From there, through the commissioning or retro commissioning processes, our data is used to inform design for upgraded systems. During the commissioning process, our assessments are used once again to verify that, yes, the systems have reached optimization. They're also used for the testing and balancing portion, for the engineers to understand where final adjustments in airflow and balancing need to occur to confirm building optimization. Lastly, all of this data, along with calculations using the equivalent air change per hour calculation from ASHRAE, is all sent to UL to obtain the UL ventilation and filtration mark. And this is a new mark that UL has come out with. It uses our Veridart assessments to understand whole building HVAC verification. And so we test 10% of high density areas like conference rooms, classrooms, et cetera. And we're measuring percent aerosol removal. Buildings and these high density areas that achieve 99% or greater of aerosol removal within an hour, it links to about an equivalent air change rate of 5. And if the building systems are shown to reach this criteria, which is currently the only criteria really out there regarding HVAC systems and airborne pathogens, they will then issue a mark, which now becomes your communication piece to your occupants, that not only have you optimized your systems and you have data behind that, but now UL as a third party is putting their mark and their stamp on it, saying, yes, we have verified that these systems are in fact operating to this criteria. And now this becomes an easy way for you to communicate by displaying this mark in the entryway of your buildings through your communications and emails, marketing communications to your occupants, that you and your building have met this criteria and put in the effort. So that is more of course detail on that, but thank you, Steve, for letting us chime in here. And back to you.
Great job, Stephanie. Well, I really appreciate all the speakers today. We have run over a little bit on the time, but we are going to continue on with our question and answer period. So both Travis and Randall are standing by. They're not going to be too mean to our speakers, but they did promise some intriguing questions. So Randall, would you like to start?
Sure. And I think, I was jotting down a bunch of questions, but one that kept coming back to that kind of spans across all the discussions was, it seems like the crux of some of the issues, especially here at Goldman Sachs, the health and safety of our employees is paramount and priority number one. But, there's also some competing priorities in terms of our ESG and energy reduction goals, which, I think was spoken to quite a bit. But, we're really trying to start to look at different strategies for understanding where that additional ventilation and filtration has a point of diminishing returns, such that, going with an incremental CFM of outside air costs me more energy, but doesn't actually have a health and safety benefit that's, measurable. And so those are two competing priorities. But then the third one that, I don't think we really spoke about today is, cognitive functioning in spaces. We talked a lot about health and safety from a virus perspective and a sickness perspective. And so prior, just giving a little more background, prior to the pandemic, we were working with the likes of Doug Mass and Costantini and Dr. Allen, who I was referenced a few times as well, on should we be bringing more outside air just from a cognitive functioning perspective, not a pandemic perspective. And so we're really trying to find that happy medium, and perhaps, the real-time air monitoring is the way to do that. But curious what other strategies you guys have been kicking around in terms of finding that sweet spot that meets all three of those.
Well, maybe Doug, you could start off talking a little bit about energy and providing good recirculation, and then maybe Dr. Bill, you could follow up on cognitive functions about bringing more outside air in. So, Doug.
Yeah, that's the quintessential question. What do we do here? My sense is always that we want to have superior air filtration. That's always been something that based on the science and the data that I've seen about the flu virus and transmission, et cetera. But I also see that the energy part is critical. So one of the new tools we have, and I'm not here to plug or anything with Safe Traces, but there is now a way to validate how much of the aerosols and whatever's in the air is removed. And if we test the system, and then with full, 20 CFM, or 0.2 CFM a square foot, whatever we'll bring in with high filtration, we can always do an experiment and just cut back on the outside air a little bit. or change the filtration and see what the removal rate is. So I think there's more work to be done, and there's no single answer right now. But for now, the default, I think we need to stay where we are until we get more information. That's the way I look at it. Dr. Bill.
Sure. Well, this is a complicated issue. More outdoor air may be helpful, but of course it may be one of your main sources of fine particulate matter, which is maybe the contaminant of most concern overall indoors. It can be a source of ozone, and we know that it has a heavy energy penalty. So, I think the important thing is understanding what it is we're trying to control. I think we rely on ventilation so much because we don't actually know what's there. So we just correlate more ventilation with maybe outcomes that we like. As far as cognitive function, I certainly believe that there's scope to increase outdoor air to improve it, but I don't know that we really know exactly what it is that's being controlled by more ventilation. The studies by Satish and Allen and others have suggested that it's actually the absolute CO2 concentration, but then Technical University of Denmark did some experiments that try to replicate that, and they didn't really get cognitive function deficits unless they were also in parallel increasing the bioeffluent from people. So we're not entirely clear on it. We just know that more ventilation would probably help. But I think focusing on specific contaminants, the main contaminants that we find indoors, things like formaldehyde and particles, and using air cleaners to some extent to mitigate those is going to help. And also, I did one more thing I mentioned, and it wasn't discussed later, personal ventilation. With the outdoor air that you're going to bring in, if you have a workplace situation where you can deliver clean air right to where someone's sitting, that can give you a reduction in required total outdoor air that's comparable to having a perfectly functioning displacement system, if you look at the correction factors in ASHRAE Standard 62, for example.
Yeah, that's great. Thank you. I think, it's about delivery system. It's about understanding better what component of the outside air is really contributing to the COG-FX functions, and perhaps finding other ways to remove those contaminants without actually just flooding the building with incremental outside air.
And Randall, given your international portfolio, each city is going to have a different requirement where we're bringing the air in from. Is it fresh air? Is it not fresh air? So I think it's different solutions for different locations, but there should be a minimum standard, I believe, for your employees worldwide, so they have a safe and healthy indoor environment.
Sure.
Travis, I'm sure you've got some good questions for us. You're on mute right now. There you go.
It actually probably just boils down to one question. So I used to work in the garage with my dad, and his rule was measure twice and cut once. And then he measured more than twice. He would measure twice before he cut, and then he measured 3 times after he cut. The most disturbing trend I see in IAQ and ASHRAE and our HVAC societies is that we'll cut. We're always recommending cutting, and we never measure. We don't measure before, we don't measure after. So I love the last 2 presentations, and frankly, I cringed through the first couple of them. I'm in the middle of our return to office conversations right now, and we are not willing to condemn 100% of our buildings and say that we need air quality interventions across the board. So what I really need right now is, how do I know which buildings need interventions? And how do I know which interventions fit which buildings? How do I know which ones need filters? How do I know what proxies do I use to make those decisions? What levels are we interested in? And then most importantly, if I'm going to invest in air quality interventions, what are the pre and post measurements that I use to make sure that those interventions worked, to make sure that I got what I paid for when I did an air quality intervention on a building? So the way that I'll phrase the question is this: if I give you a portfolio of 50 buildings, and I have a budget to do air quality interventions in 20% of them, how do I know which ones to intervene in? And how do I know which interventions to choose?
Who wants to take a stab at answering that one? That's a good question.
Should I jump in there, Steve, just quickly?
Please, Andrew.
Because I think
it's an
technology.
one. Yes.
because my starting premise, you can't control what you don't measure, is absolutely right. You have to have some measure of it. And I think personally, for us, if I talk personally from our perspective, we're the same as anyone else. We have offices around the UK. We had to return to them post-pandemic or towards as lockdown released. And in fact, the pandemic was almost, I wouldn't say godsend, it's never a godsend to anybody, but it enabled us. There was two things that it caused us to do. One of them was to put in place a track and trace system, which meant that we knew what the occupancy of all our offices was at any one time.
Yep.
The other thing, it encouraged us to start using the indoor environmental monitoring systems that we have in place, some of the ones that I was just mentioning, and actually looking at the correlation between those two. And I think that's what's needed. It needs, as a fundamental understanding of how does occupancy as a starting point impact on your indoor air quality.
So Andrew, by the way, your presentation should be first. I mean, we should absolutely, I don't know how you're going to present this to the public, but I was totally on board with you. And we're right in the same neighborhood as you. It is much more effective for me to go into all of our buildings and measure PM 2.5 and formaldehyde and all those variables that you measure than to go out and buy MERV 14 filters for everybody, right? So and I know you and I did, just to say, you and I didn't meet beforehand, but whatever they're paying you, double it and promote this guy to the lead of the team.
Okay, with that, thank you for that. And then you were talking about the interventions. Well, that's where the specialists within the high performance building group, we understand the interventions and we are testing interventions to see what differences they do make in real terms. So,
I also want to add to that conversation, if I can, in what we're doing as a company and helping people obtain that data and information as the baseline and understanding impacts of different scenarios, whether it's filter levels or outside air percentages, CFM, and on a portfolio approach is really helping, the client prioritize their buildings that they know may need some help, or they want to verify through recent upgrades of understanding that where the upgrades they needed or they made are working as they intended, and then using that information to understand, okay, we want to get the rest of our buildings up to this parameter. How do we do that? What do we need to change or adjust so that we can reach that type of standard? But again, it's going there, understanding your baseline assessment of how are these systems functioning, where can there be targeted improvements made to optimize that capital expenditure and energy consumption.
I'm going to interrupt you with a pushback question.
Sure.
I totally understand your technology, and I've talked to your company since they were formed, and I get it. Here's the question there. What Andrew was just talking about, we can do some very simple and very cost-effective air quality metrics, right? With PM 2.5 and PM 10 and CO2 and all this other stuff. Your system is a significantly more expensive air quality metric that has to do with decay rate of bioaerosols. My question for you is that out of that portfolio of 50 buildings, I'm guessing that 45 of those buildings don't need a bioaerosol decay rate test, and they can be done with the simple metrics. So when is it worthwhile to deploy your system? We have to recognize that that's sort of an upper echelon measurement system that's probably not applicable to everything, right?
I might interject here quickly, because we've done this for other clients. And what we've done is we've taken one of their facilities, and they have hundreds and hundreds of similar types of facilities. And we tested all types of different rooms using both CFD modeling and the Safe Traces technology. And from that, we determined where there were risky spaces and where we were doing a good job, or how we could change the operation. So one example is we learned that operating the overhead fans at high speed was far superior than operating them on low speed, which is the way they were operating it, right? So that could be applied to all of their facilities worldwide, globally, right? So you can't afford to go ahead and test every room in every facility, but you can afford to test samples of types of rooms to identify where those problems are occurring, what the simple measures are to improve the operation, and then do that on a portfolio basis. So I also think the sensors that you mentioned, Travis, and let's give you some credit for your hairspray technology. If you haven't seen the reports of the studies that Travis has done, it's really quite amazing. He's been using, simple things like hairspray to test the efficacy of ventilation in rooms. And I think it's important information he's sharing with us.
Yeah, I would also like to add too that we're an absolute complementary portion to what Andrew was talking about on the real time. So whereas you're not doing our testing all day, every day, it's important to have those measurements from that real time instruments to understand that those other parameters that are happening. But we do take care of that aerosolized portion and understanding of the buildings. Our approach has changed probably since we've last talked, Travis. So we'll have to get together.
Yeah. And look, spoiler alert, I'm very familiar with that UL the validated Healthy Buildings program. If we're going to buy anything at this point in time, we're going to buy that.
Yeah.
And we're going to have UL go out and assess, a fraction of the building. So I'd be very interested to see if there was some way that your technology could integrate to a sampling of those, like Steve just described. I think that's where that's where the smart money is.
I'd like to comment, since I was one of the first two presentations, and I'm not sure exactly what was making you cringe, but also I'm happy with what I'm being paid, so I don't really care. But there actually is a lot of evidence that, say, increasing ventilation rates has resulted in various improvements for many facilities. The problem is what's going to happen in mine. And would also add, it's a prescriptive world. Almost everybody just wants to be told, how much outdoor air do I need? What filter should I put in my system? And you're going beyond that to performance, which I think is where we should go. We've already got a newly approved list of 15 contaminants that ASHRAE says need to meet certain requirements in the indoor air quality procedure. So that's a list of things you can test for. And actually, probably only a couple of them are really important: particles and formaldehyde, maybe something else. So I'm really kind of on board with the approach that you're recommending. And of course, you do that and you baseline. I think modeling has a place to play, or part to play in cost effectively extending a certain amount of actual measurement. But ultimately, I'd like to see buildings controlled real time by the key things. And this is one of the research questions: is exactly what is that set of things that we ought to be monitoring, and to what levels. So we think we kind of agree there.
I don't know how much time we have left, but it's kind of a nice segue into a question I had, kind of about controls, right? So, similar to Travis, I think I have a fairly large portfolio, a couple hundred sites, and obviously, we build new sites, we develop new sites, and that's easy. We can size the systems, we can design the systems to do this, but we have a lot of sites where we have existing systems that were sized and designed prior to COVID being, a thought in anyone's eyes. So we're really looking at sequence of operation and control strategies within the current, MEP footprint of our facilities to see how to do that. Some of the things we're looking at is perhaps using real-time, people counter sensors in lieu of CO2, which is a more real-time reaction to people in the space as opposed to the lagging indicator of CO2. But one of the other ones we're looking at is looking at how we size units and how we leverage the units that are already sized in such a way that maybe we go 30 CFM of outside air per person up to a ASHRAE 3-degree day. Then once we get to the 2-degree day, the 1-degree day, we start to go from 30 CFM to, but never below the, ASHRAE plus 30% lead requirement, but we scale down such that we don't have to have such an energy penalty while still being, and the beauty of that is that most of the degree days are in the summer when our occupancy is lower anyway, so we're trending our occupancy against that, and we usually don't ever get to the point where we're below 30 CFM. Are there any other sequence of operation changes you guys have successfully implemented that has helped where you have an existing constraint within MEP sizing?
Let me add a flavor to Randall's question, because I like where he's going, and we've talked about this with our internal EH&S team. We have a lot of environments where we spend a lot of hours in economizer. And so if you were to look at air quality of a building on like an annual average over a 2,000 hour work year, if you spend 1,000 hours of that in economizer, then the sort of health outcome portfolio of that building is kind of different. And it sort of addresses that idea that on the hottest day of the summer or the coldest day of the winter, okay, I'm going to sacrifice some IAQ, so I just wanted to layer that on there.
Yeah, that's exactly the mindset and the lens through which we're looking at it. That's kind of where my question's coming from.
Well, I think one of the things that we're doing for clients now is we're setting up their buildings with different program modes. So there's, used to be we had an operating mode and an off-hour mode. Now we've got a fire mode, that automatically switches the buildings into modes if there's outdoor forest fires. We've got a low energy mode. We got a pandemic mode where we bring in more outside air and increase recirculation rates. These are easy things that we can, plug into our control system. So Andrew's going to be talking about this and many other items on September 22nd. We think this is an important issue because, yes, we need the ability to bring more outside air in certain times. But when we don't need to, we need to be able to cut it back to save the energy. Yes, we need to be able to recirculate more air through MERV 13 filters when there's particulate in the air. But when there's not, then we can reduce that recirculation rate. So we're going to have to use technology to offset the increased energy by creating these healthy buildings that our clients are looking for.
Hey, Steve,
sorry, if I just jump there quickly with one other example. We're talking about modifying the system's performance. There's another way of going about it for certain types of building that we're involved in, which is modifying the human actions. And this is real-time air quality monitoring, and this is for visitor attractions, whereby you divert people off to areas of good air quality from bad air quality. So in actual fact, you actually get the same result, not by changing the systems, but by changing where people are going and how the building is performing in response to where those people are. So that's just another interesting way of looking at it. But obviously that only works for visitor attractions and things where you've got the public going in and moving around areas.
I just have one final comment, which is if Travis, if your group owns the building and operates it, and Randall, if your group owns it and operates it, we're going to get an assured performance, or hopefully an assured performance. But a lot of your portfolio and other portfolios are leases, and we can't control it. So I think what we've been doing recently is on all of our lease reviews, where they give you some basic parameters, this temperature and this much outside air, we're going in and asking them to give us their control strategies. I mean, that's what's important too. And one other anecdote, many years ago, my kids were at a school, 300,000 square foot building in New York City. And they called me in to sort of help them out. And I said, let me talk to you about filtration, et cetera. And I went into these big air handling units with their chief engineer. And I said, where are the filters? And he said, what filters? So my kids went to a school for 12 years that never had filters on the air handling units, and they're still around. My point is, we have to be more vigilant when we can't control what's going on. That's another factor to think about.
So Doug, I think where the lease conversation is going, and I'll be honest, we've already had this, is to couple it back to where Andrew's at, he may have already heard of this, is that you could actually have a lease with a landlord that's structured based on, like right now, our leases say, I'm going to lease the space from you, Mr. Landlord, and I expect that space to be 73 degrees, plus or minus 3 for the hours of the year. That's what you owe me as my landlord. We could just as easily say, I expect that space to be 800 ppm of CO2 plus or minus 200 every hour of the year. That's what you owe me as the landlord. Or I expect my PM 2.5 to be 12 plus or minus 3. That's what you owe me as the landlord. That's the kind of recommendation I'd love to see you guys,
Sure.
getting in there. That way tenants, and that conversation is already happening, by the way, with the Googles and the companies that are organized where their environment is part of HR, that healthy environment metric, that conversation is well underway.
And to add to that,
I know many building operators in the past, they used to get rewarded as the energy cost goes down, they get a bigger bonus, trust me, and they shut that outside air. I've seen it all.
I think building owners are really open to complying with these requests, because they need to keep their tenants in the buildings, and they're seeing such a decrease in tenancy that it's really the tenants have the power right now to make these types of requests.
Well, I think this has been a great presentation. We'll go ahead and finish up now, but we will be distributing the recording. We will be distributing the presentation, and we look forward to the follow-up that Andrew's going to lead on September 22nd, talking about how advanced controls can reduce energy and still provide outstanding indoor air quality. Thanks for our speakers and guests today. Have a wonderful week. We'll talk to you soon.
Thank you.
Thanks, everyone.
Thanks, Steve.
Thank you.
Thank you.